Welcome to Brain Vision.
Okay, so we're doing chapter 26, problem 49. So we have this circuit here which has all the resistors have the same resistance, big R, and it says at time equals 0, the capacitor C is uncharged and the switch is closed. And it says at time t equals 0, the three currents can be determined by analyzing a simpler but equivalent circuit. Identify this and use it to find the values of I1, 2, and 3. So if the capacitor is uncharged, there's no voltage drop against it, which means it's just like the capacitor doesn't exist. So for part A, the simpler circuit looks like this. It's just the same thing without the capacitor. So it will look like this with R, R, and R. This is EMF. So we have I1 going this way, I2 down here, I3 over here. So now from this simple circuit, we can figure this out. So first of all, we should know that we can figure out the REQ for this. So we have one resistor here and then two more added in parallel from that. And these two parallel ones are in series with the first one. So that means this is R plus the parallel branch, and these are in series. So we add these up, and this becomes 3/2 R. So now using the loop, or Kirchhoff's loop rule, we know that I1 is given by EMF over REQ. So in this case, this is just 2 EMF over 3R. So this is I1. And now we also know that I1 is going to equal I2 plus I3, because if we look at this junction right here, we have I1 coming in, and I2 and 3 splitting apart, and then coming back together here. So from that, we should also know that I2 equals I3 because both branches have the same resistance. So based on that, we know that I1 equals 2 I2, or I2 equals EMF over 3R, which also equals I3. Cool. So that's everything for part A. Move on to part B now. So part B says we're now at time equals infinity. And it says the currents can then be determined by analyzing a simpler circuit, identify the circuit and implement it, and finding I1, I2, and I3. So part B. So now at time equals infinity, the capacitor is fully charged. So there's no current going through that branch at all. So the simpler circuit is by just eliminating that branch, meaning we just have a circuit here with two resistors in series. So from this, we can see that REQ is just 2R. So now I1 equals I2 because we just have one loop here, nothing else. And this equals EMF over REQ, or EMF over 2R. And since we already said there's no current going through this other part, we know that I3 equals 0. Awesome. So now part C. Part C says, what is the potential difference across the capacitor? Well, we already know there's no current going through here, right? So we know that I3 equals 0. And if there's no current through the resistor, that means the voltage drop across the resistor is 0, this resistor. So let's come back down to this drawing for part B here. So if we have a voltage drop here, there's no current going, so we know that the voltage along this branch must be equal to voltage along this branch, because that's what happens when we split up in parallel. We have to have the same voltage drop across each. So that means we can say the voltage in the capacitor drop in the capacitor is going to be equal to the voltage in this resistor right here. So if we set that equal to each other, we can know that the voltage is just I2 times R using Ohm's law. So if we replace what I is, we see this is just EMF over 2R times R, or the voltage in the capacitor is just EMF over 2. Awesome. Looks like that's everything.